Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy, and today we have my much anticipated review of the 45-degree sector test. So let's cue up the music and get going.
All right. So how do we test those models? Let's talk about that. So what I've developed is a test box. In other words, we're going to break those models down into a 45-degree sector. So we're going to test long distances of the globe and the flat Earth model. We can break it down. What I have before you here is what's called the test box. In other words, the center test box, we're going to use the sun from orienting station, whether it's from one observer or two observers, and we're going to measure sun angle, easterly or westerly. Okay? Now, you'll note that there are red dotted lines. What are these? Oh! You get an A. Look at that. Woohoo! All right. See, that wasn't so hard. There's the line of parallel, man. I know it. If I learned anything, I learned line of parallel.
Well, I'm glad that somebody knows what a line of parallel is. We all know what parallel lines are, but what's a line of parallel? Now, he says that the dotted lines here are all lines of parallel. Well, let's see. That is a parallel line to that, and that is a parallel line to that. What are these lines parallel to? They actually kind of look perpendicular to me. I'm not really confident on Mr. Kell's geometry skills, but we're going to let him go on.
Yeah, all right. So you'll see here we have the sun, and it's timed. In 3 hours' time, we're going to measure sun angle from our sun survey point. Our sun survey point is going to be put in at a certain time of day when the sun is 90 degrees to us. How do we do that? I got to know how to do that. We can do it, and I'll show you how. It's easy. Piece of cake. So all we're going to do from that sun survey point, we're going to measure 3 hours from that sun survey time, and we're going to measure direct sun angle from our orienting station. Once we do that, we can start to determine whether we're taking that reading from a flat surface or a curved surface. So if that measurement is 45 degrees and below, indistinguishable. But if it's 46 or more, we've got problems. That's a flat surface. Sun's too high in the sky.
So we're going to take 3 sets of readings. One is going to be at solar noon, when the sun is directly 180 degrees from our observer position. We're going to go 3 hours before solar noon and 3 hours after solar noon. And we're going to use 2 different days. The first one's going to be November 30th, simply because that's about the time that I started working on these videos. The other one is going to be the 4th of July, because America. We're going to get the information from 2 sources. Now, I'm going to show you one of them, but I did the other on my own. The first source is going to be a planetarium program called Stellarium, which is what I use to point my telescope at objects in the sky. That gives me the exact coordinates of the sun or any other celestial object on any day at any time. The other one is going to be time and date. Now, Stellarium is a free program. Time and date, let me show you how to do that. Okay, so here's time and date. It's at timeanddate.com, and then you can put in your zip code. In my case, that's 48858 from Mount Pleasant, Michigan. You can put any location in here you want worldwide. Then what we do is we go down and we search for July of 2021 and go down to July 4th. Now, according to this, the sun will be 180 degrees to Mount Pleasant, Michigan at solar noon, which is at 1:43 p.m. So Let's go ahead and write those numbers down. Now what we're going to do is we're going to take 3 hours before, which will be at 10:43. Well, there's 10:42, that's close enough. So we see the sun is at an altitude of 47 degrees, and it's at a bearing of 104 degrees. And you can see those. They're listed right here. At solar noon, the sun is at 69 degrees and 180 degrees. And then our next one is going to be at 16:43. And we'll come over here to 16:43. That's 4:43 in the afternoon. And there's pretty close. There's 4:44. I think that's close enough. Looks like it just does it in increments of 2 minutes. But that's 48 degrees. And it's at a bearing of 255 degrees. Now what we'll do is we'll go up here to November. Hit go. And then we're going to come down here to the 30th, right there. Now the more astute of you will happen to notice a little difference between those two, but we'll go over that a little bit later. Right now it says that the meridian is at 12:27. That's solar noon, and the sun is at 25 degrees and 180 degrees. So it's at an altitude of 25 degrees and it's due south of our location. We're going to go to 9:27, 3 hours prior, and we've got an altitude of 13 degrees and a bearing of 138 degrees. Now we're going to go to 15:27, which is 3:27 in the afternoon. We're at 13 degrees. And we're at 222 degrees. That's the azimuth to the sun. So once again, on July 4th, it's 10:43, 13:43, 16:43. In November, it's 9:27, 12:27, and 15:27. Recall that this is daylight savings time, and this is standard time, which is why there's about an hour's difference between each of these readings. But I do want to call your attention to a couple of things. First of all, look at the difference between 180 degrees and 3 hours before and 3 hours after in the summer. Likewise, here in November, 180 degrees. Look at the difference between 3 before and 3 after. Likewise, look at the difference here in the elevation of the sun and compare that to this elevation. Now, if you would, recall what we just did. Think about the 3 hours before, the 3 hours after, and the fact that it's solar noon, not clock noon. And this is 180 degrees true, due south. It's not 180 degrees magnetic, because you have to measure things by true direction astronomically, rather than by magnetic direction, because the magnetic pole and the North Pole are not located at the same spot. That's why you have to take into account magnetic declination. And any good artilleryman worth his salt understands the concept of magnetic deviation.
Let's talk about the test box for each model, the flat Earth and the globe. And basically you'll see a series of 2 numbers within the test box. The bottom number is the observer angle. All right, the observer angle, what the observer is angled or oriented to the sun at 3 hours. So in the globe model, the observer is oriented 45 degrees. Now I know some here say, well, you know, it's not a perfect sphere. Well, guess what? If it ain't, that's the best case scenario.
Now hold on there a second, Haas. The angle to the sun at 3 hours before and 3 hours after is 45 degrees on the globe? We just got the angles. No. The first angle is 76 degrees, and the second angle is 42 degrees. Did you ever actually do this test?
Because if it's not a perfect sphere, you're in bigger trouble. Because your angle is only going to increase. How you figure that? Geometry, dude. You ought to try it. All right. So at 3 hours, the observer on the globe model is 45 degrees. Okay, we need to remember that. Observer orientation. The top number is the maximum measured angle to the sun from that observer. That's the maximum number. You'll note that both these numbers equal what? What's 45 and 45? 90 degrees. What did we have as a guide angle in our example? Man, y'all are all over it this morning. Great, that's great. 90 degrees. 90 degrees is the maximum. That is the standard. The flat Earth model, now you notice a difference. We got what as the observer angle? 0 degrees, right? How come it's 0 degrees? I'm on a flat surface. It's flat.
You know, one problem that I have with people that are trying to tell me why the globe model is wrong, yet don't understand what the globe model is, it kind of jumps out at you when you listen to him. Now, notice that he said that you had to have 45 degrees at 3 hours before and after solar noon. He said clock noon, but what he really meant was solar noon. Now, it's true that the Earth will rotate 45 degrees in 3 hours. And what he says would make sense if it was the equinox and you were on the equator. You would get a 45-degree shift in your angle to the sun. However, there's another thing the Earth does. It tilts. And in July, the northern hemisphere is tilted in this direction. And in November, the northern hemisphere is tilted down in this direction, which is why it is now summer in Australia, although we're getting ready to go into winter here in Michigan. So in my book, he's already failed his test because he didn't adequately model the two different models. He doesn't understand what's going on the spherical Earth. So let's continue.
What's my top number? Man, I got a whole 90 degrees to work with, measured sun angle. Guess who's got the advantage? Flat Earth. Hey, heliocentrists, they'll complain about that. Well, you know, that's not a fair test. Hey, dude, you chose a sphere, not me. No, I'm just going to tell you how to test it. Break it down geometrically. You pick that model. You pick that winner. That's your horse. You got to ride him to the finish. Okay, the test box, the globe. All right, so they're telling us that the sun, the Earth rotates around the sun. Okay, here's how we break it down. 45 degrees. This is the 45-degree sector test box. In other words, I want you to remember 3, 4, 5. 3 hours equals 45 degrees. You are oriented 45 degrees from the time of survey after 3 hours. There are 8 sectors within the globe model. 8 times 3 is what? 24 hours. Guess what happens when you put that sun survey point 24 hours later? Guess where Mr. Sun shows up? Right at the survey point. That's something else they don't like. They're like, man, let's stay on the survey point. I never heard of that. What is that? FE test box, flat Earth. Basically, the sun moves over the flat surface of the Earth. Pretty simple, really. We just break it down. It's 45 degrees, like a pizza. All right, so now we got the same thing. 3 hours equals 45 degrees. Put our sun survey point in, same standard. The only problem is, if you look here, this is the advantage. I got a full 90 degrees to work with. And that's a heavy advantage.
Now here's a very interesting date and time, and this is Equatorial Guinea. And on a particular day in March, we have what's called an equinox, and it occurs on March 19th. I want you to notice that sunrise occurs at 90 degrees, and sunset occurs at 270 degrees. Let's have a look at these sun values. Now, solar noon is at 12:32. 3 hours before that would be 9:32. And 3 hours after would be 15:32. Now, let's go see if we can find out where the sun's going to be on at those times. So the first one that we said was 9:32. That's pretty good right there. So the altitude will be at 45 degrees. And the heading will be at 94 degrees. At the meridian, it will be at 86 degrees, almost overhead, reflecting the fact that this is within 4 degrees of the equator. And it's at 178 degrees. Looks like it goes from 178 to 184, so that's closer. There's 332. It's 45 degrees, and it's at 266 degrees is our azimuth. Now let's just leave it on that for a second. So at solar noon, the altitude is 86 degrees, and 3 hours after, it's at 45 degrees. So that's a 41 degree difference. The heading at solar noon is approximately 180 degrees, and 3 hours later, it's at 266, which is 4 degrees off of 270 due west. So his 45 degrees doesn't even work at the equator. Okay, so the bottom line is that even at this stage, his test completely fails. He has no idea what's going on an actual globe Earth. The numbers don't match because he has presupposed a flat Earth and tried to figure out what it should be on a flat Earth. He didn't take into account the curvature of the Earth or the tilt of the Earth's axis. So let's go ahead and continue a little bit more and let him dig himself a little bit deeper.
It's the model you chose. You chose a sphere as one of the hardest geometric forms to validate. This is how it works against them. Don't let this diagram confuse you. It's a pretty busy slide. You'll see it on the website. And you see here, when we look at, represents the Earth and the Sun, you'll see that the black arrows represent line of parallel. This is our survey point. Our measured angle, we can come from our measured angle either way. Okay, we have one observer or two observers, simul or stow. And all we're doing is the red arrow represents 45 degrees. Could be either flat or a curved surface. But once you go beyond 45, you go to 46 degrees, you do the math. The measured angle over here, 46 degree angle, 45 degree curve or surface, 91 degrees. You now exceeded that by 1 degree. This is how far off line of survey the heliocentric model is once you put the survey point in, the sun survey point. Oh, guess what?
I'll bite. Guess what? Let's see what we figured out so far. First of all, you can't do math. I have no idea where you got 1.6 million miles equaling 1 degree. You don't show any of that. And there is absolutely no mathematical formula that will give you that. Second of all, I want to draw everybody's attention to the distance to the sun. 93.879 million miles. I thought it was 3,000 miles. Finally, look up here at his diagram. Now, this is something that you actually have to think about a little bit. What are we looking at here where his head is? That's the North Pole. What is the outside edge of this sphere Earth that he's drawing? That's the equator. I'm sitting up here at 45 degrees north. My angles are not the same as his angles, for obvious reasons. They're much closer on the equator, but they don't even match there. Now, the final thing that I want to draw your attention to is this orange line right here. This is what he thinks the angle to the sun will be 3 hours before his noon sighting, or 45 degrees off his noon sighting. That's a local sun. That's a mistake that he is making. This would be the line to the sun, not that. Because the sun's rays arrive at Earth in parallel. That's what all celestial navigation is built on, and you can easily confirm it for yourself simply by holding a tennis ball up to a moon and noticing that the phase of the moon and the tennis ball are exactly the same. It is becoming very apparent to me and any other thinking person that this gentleman has no clue what he's talking about. If this gentleman claims to be a master gunner in the United States Army and says artillery does not take into account either the rotation of the Earth or the curvature of the Earth, and this is his ability to do geometry, I really don't think that he was in charge of the gun. You know, those breeches don't polish themselves, and the projectiles and the powder bags don't carry themselves. I think that's more what he was doing. This gentleman is certainly not aiming octillery, or at least I hope he's not. Okay, so the bottom line on this test is that Mr. Kell has absolutely no understanding of what he would expect to see on a globe Earth. Therefore, he designed his test around something that he came up with on his own that has no bearing on reality. You know, it seems that every time a flat earther sets out to disprove the globe, they end up instead proving it. Mr. Kell is no exception, and we'll see how that works on Monday. So this is Bob the Science Guy signing out from Northern Michigan. I want to thank all of my Patreons, channel members, and subscribers, and I'll see you again soon.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Bob the Science Guy. Bob the Science Guy.